Welcome back to memorization. So we're going to get a little bit into geometry now. Sum of interior and exterior angles. So for the sum of interior angles, we have a formula which is n minus 2 in parentheses times 180 degrees, where n is the number of sides. So triangle, 3 sides, 3 minus 2 is 1. 1 times 180 is 180, and we know that a triangle is 180 degrees, so that checks out. The sum of exterior angles is 360 degrees. I know some people are confused by this. You can prove it to yourself. Just draw some strange shapes, calculate the interior angles, and extend the sides to see that the exterior angles will always equal 360. If you want to prove that to yourself, it's kind of interesting. Next, we have lines, parallel lines cut by a transversal. So this idea is, you just have two parallel lines and we cut them by another straight line. If we do this, we know that a line is 180 degrees. So A plus B is 180, C plus D, E plus F, G plus H, all 180 degrees. If we move this green line up, it would be the same line as the blue line. So, I mean, obviously, E and A would be the same, F and B would be the same, what have you. Also along the same lines as A and B must be 180 degrees, if the black line is straight, A and C must be 180 degrees, E and G must be 180 degrees. And with that being said, we can, by moving the line up, we can say that A and D are the same, E and H are the same, G and F are the same, and C and B are the same. If you want to have a deep understanding of that, there are proofs and whatnot for that. But I mean, it seems like a fairly easy thing to just memorize and move on. You're not going to really be asked to provide geometric proofs like you would be in a geometry class on the praxis. Next, we've got sectors, segments, and arc angles. So this is just vocabulary. A chord is a straight line segment with endpoints on the circle. So if we took, I'm using A as this point over here. So A, B, both of the endpoints are on the circle, so this is a chord. An inscribed angle, angle created by intersection of two chords. So BAC would be an example because B and A, BA is a chord, CA is a chord, they intersect right there, so this angle right here must be an inscribed angle. The central angle is an angle created by intersection of two radii, so the plural of radius. Really all it's saying is it's an angle that comes off of the center of the circle where the endpoints are on the circle. And BOC is an example of this. A arc is a portion of a circle's circumference. Example is the black line BC. So the BC could either be this orange line here or the black line that goes around. We're talking about the line that goes around. So the actual line on the circle. That is a arc. The sector is the shape created from central angle and arc. An example is OBC. So this whole slice of pizza, if you will. So we're including this little piece right here. And then a segment is a shape created by a chord and arc. So an example, a shape outlined by BC and arc BC. So this little sliver right here, that's the segment. So now that we have our vocabulary down, we can take a look at these formulas. Given that O is the center and angle BAC is an inscribed angle, then angle BAC is equal to the angle BOC divided by 2. So it's just half, right? This angle is half of this angle here. Is all that's saying. and angle BAC is equal to the arc angle BC. So if we then look at it, we can see it right there. And BOC is, or sorry, yeah, angle BAC is the arc angle BC divided by 2. So same relationship as we had here. And then if we extend that further, then arc BC must be equal to BOC, right? If BAC is equal to half of either one of those, then those two must be equal to each other. Arc BC length, so we're talking about the arc, again, the black line, is the angle BOC times a radii. So that would be, like an example would be OC. And that would give you the length. Sector area is the central angle in radians. So be careful of this. These formulas do change if we're not talking in radians, and I'm generally going to speak in radians. Times r squared over 2. This formula is actually bigger if you look at it like academically, but I did all like the canceling out for you so that it'd be more simplistic. Segment area is the sector area, so what we found here, minus, so I know this is normally thought of as like change, this is triangle OBC. So the area made up by, we should actually change that, area of OBC will give you the remaining sliver. Inscribed angles and tangent relationship. So we found out the inscribed angle definition earlier. If the inscribed angles, these angles will always be the same. It doesn't matter if like these are of equal length. So they're meeting on 3 different points in the circle, that's fine, but where they end up is always the same. If that's true, then the line tangent to this point where they all meet creates the same angle here as these inscribed angles. Then I will get into triangles in the next video.